Okay, great. All right, hey everyone, welcome to another deep learning lecture. So we are getting deep into the heart of our deep learning material, and we're starting a little bit late today because we just had one of our top submitters for the Auto Lab Autonomous Driving Competition share her solution, and it was really cool. So thank you again, Pooja, for sharing. And now we're going to hop into lecture here. We've got a bunch of stuff to cover today. Let me go ahead and share the schedule just to make sure that you've got the right things on the top of your mind here as we get into another week of computer vision. Have I shared the right screen? Yes, I have. Okay, cool. So here's the course schedule. As you know, we've made it to here. So we're really getting into the heart of deep learning now. We're going to finish up some fast AI stuff from last time, but this lecture and the next lecture, we're really going to get into the nuts and bolts of how these deep neural networks work. And you've already learned about neural networks in general, so I'm hoping that's really going to give you a nice deep understanding of this stuff. Just a reminder, project stage 3 is due a week from yesterday. If you're in a group that's having trouble getting data or feeling behind, please come talk to us. You know, in some cases we may be able to give you an extension if it makes sense for your app, for your problem. We know some industry partners can be slow. We really want you to succeed, but we can't help you if you don't talk to us. So make sure you come schedule meetings with us. We've got these open meeting slots this week, and you are required to meet with us, so that's part of the course. So make sure you get these meetings scheduled, and we're here to help. So stage 3 is coming up. You should be working on modeling. I highly recommend using fastai if you're doing a deep learning project. There are some cases where fastai might not make sense. Like we had a meeting with a group last week working on privacy, and some of the better privacy libraries are in TensorFlow. So in that case, it wouldn't really make sense. But in many applications, fastai is going to get you going pretty quickly. So you should be full swing on your projects. We've tried to make the rest of the course not too bad. So you have a programming challenge, but it's not as bad as the last one. And then you'll have a quiz on deep learning, but again, nothing to be too worried about. A lot of your focus should be on your projects. That's where I want your main focus to be. And then in the final module, we'll have one more quiz and one more challenge. But again, these are not terribly difficult. You've made it through the hardest programming challenge. So do take that extra time and bandwidth you have to work on your project. And I hope that the things we're covering in lecture, they won't be relevant for everyone. Some projects are focused more on analytical computer vision or key point detection, things like that. And for those folks, you know, you guys will need to get a little bit ahead. We have a couple groups working on these areas, and that'll be covered in the next lecture series. But for a lot of you who are using deep learning, I hope this series of lectures are really relevant to what you're doing in your projects. That's how we've tried to set up the course here. Okay, so without further ado, let's go ahead and get into it. So we need to spend a little more time in fastai, and then we're going to get into deep learning in depth. And just a little bit of context here. So I've kind of flipped this module on its head. So if you take the time to read any of the fastai literature, so they have a book out now, they have courses out. fastai ascribes to this type of learning called playing the whole game. And it's just a philosophy of teaching. And with that philosophy, basically, the instructor gives kind of a complete working solution to you first, and you kind of play with it and break it, and then you dive down into the deep parts of it, and then you kind of come back out. In general, I don't do that. It's not quite my teaching style. My style is a little bit more start from the basics and then build up slowly. But this module, I've decided to use Jeremy Howard's approach. So what I've done here is I've really thrown you into the most, you know, this lecture, this fastai lecture that we've started last time and we're going to continue this time. This is the cutting edge stuff. Like there's no tricks. This is the full on, you know, the kind of things I want you to be using on your projects. This is the same stuff I use in my day-to-day job as a data scientist. So fastai really is the state of the art in this field. In the following lectures, we're going to be going deeper into how fastai works, but we're not going to be like building back up, if that makes sense. We've kind of made it to the top. So this really is the pinnacle of the state of the art in deep learning. So that being said, let's get into it some more. And I say that because I'm going to be doing stuff in today's lecture and in the last lecture that you saw, where I'm going to be kind of glossing over details. I'm going to say, okay, this is kind of how it works. Have a look at this, and let's get to the results, which is a little bit different than I may normally lecture. So just be ready for that. And if you don't understand 100% of what I covered, don't worry about it because I'm really throwing a full solution at you. Okay, so we left off in this notebook talking about doing object detection. So we started talking about, okay, I showed you how to get really good performance from fastai classifying images. And just for the record, this first notebook is image classification. And if you remember, we did this brick ball cylinder problem, and we were able to get a classification accuracy of like 98% or something. So a really, really good accuracy. A number of you may be doing image classification in your projects, and if you are doing image classification in your projects, then fastai is the perfect starting point. You can get very good image classification results very quickly. So even with small amounts of data. So that being said, we then went on to say, okay, what more sophisticated stuff can we do with fastai? And I wanted to just give you a flavor of how you might modify fastai or use different parts of fastai to solve different problems. So the first problem I wanted to show you was bounding box detection. And this is the idea of, hey, let me make this a little bit bigger, that's really small. Can I train a neural network to find where an object is in an image, right? That's the task. And if you are doing object detection as part of your project, I actually don't recommend using fastai. I recommend using something like YOLO. I would say there's a really good repo from this company called Ultralytics, for example. So YOLO v3, like this is an out-of-the-box object detector. It's going to do a little bit better than what we're going to do today in fastai. But if you're doing something different or more general, I just wanted to show you how flexible fastai can be. So let's keep moving here a little bit, and I'll show you what you can do with fastai to detect bounding boxes. And I'll just give you kind of a high-level overview of what I'm doing here. So we talked a little bit last time about one of the nice things that fastai does is it gives you what's called a data loader. So a data loader is a way to quickly create and set up a data set that can be used to train a deep learning model. And I'm doing that here with this method. And this method takes two arguments. It takes the batch size. And just throw it in the chat window if you remember from last time. What is this referring to? What is the batch size? What does that actually do? Yeah, what is batch size? And it's also called mini batch size sometimes. Yeah, great, Aaron. And so it's the amount of data passed through at once. Right, perfect. We're using a batch size of 64. We'll talk about batch sizes in more detail soon. And I'm also downsizing the images. I'm making them a little smaller. I'm making them 256 by 256. That can make life a little bit easier. It makes training faster. Usually starting on lower res images is a good starting point. And you can increase the size as you want as you're training. One more last little thing. So right here, what am I doing with this line of fastai code? What is this doing? And especially this part right here. What is this thing doing? So rotation, but more generally, like this get transform thing. So let me make a new cell. So does that insert cell above? No, it does not. Oh, it moves the cell. I didn't know I could even do that. Wow. Okay. What I really wanted to do was that. Okay. So yeah, so Hernan, you've said this in a nice simplified way. You've said making more images. Does anyone remember the name for that? What do we call it when we make synthetic versions of an image? Yeah, so thank you, Videhi. It's called data augmentation. And this get transforms method in fastai, this kind of spins up is not the right word, but it sets up a bunch of PyTorch image transformations. So it randomly rotates and flips and changes the brightnesses of our images. And that lets us pretend like we have more data, and it helps our model generalize. So here we're setting up a data loader with some transformations. I won't get into all the details like I mentioned, but we've set up this data loader. And this is a little bit of a special data loader because it doesn't hold a classification. Well, it does, but it also holds the bounding box coordinates of our labels, because our labels here, which are about to load, I think, there we go. Our labels also include here a bounding box. Now here's where I really want to show you kind of the flexibility of fastai. So forget about classification for a second. Forget about calling this a brick, ball, or cylinder for a minute. If we want to find the coordinates of a bounding box of one object in a image, How many numbers do we need to predict? How many numbers, throw it in the chat window, how many numbers does our model need to predict? So I see a 2, good guess. 2 would only give us like one corner because we need an XY coordinate for every point. So 2 numbers might give us this coordinate, right? And I see a bunch of 4s and I see an 8, right? Okay, so the answer is 4. So it turns out that with 2 coordinates, you can fully parameterize a box. So all you need to describe a box is the upper left corner and the bottom right corner. You could also use these corners, of course, if you wanted to. We're just picking a convention. But if you describe where this corner is and you describe where that corner is, then you've uniquely set up a rectangle and you don't need any more points. So the answer is 4 that we're looking for here. So what we're going to do is we're actually going to take kind of that default model. So we talked about this CNN learner thing last time. Let me scroll back up here. Cool. So the CNN learner thing. Remember this learner, it takes in the data loader that we made in fastai. It takes in a model architecture or a backbone. Here we're giving it this ResNet 34 model. And we're going to pass in 2 arguments, actually, really. So the first one is what's called a custom head. And again, this is an example. I'm going to kind of show you the big picture first, and then we're going to go into details. So a custom head, the idea here is that you can take a deep neural network with many layers, and you can kind of chop off the end closest to the predictions, and you can put something different there. There's a lot of flexibility. So here I'm going to put what's called a custom head, and it's like just a little section of the neural network, and it's going to let me kind of refine and do different prediction tasks than just image classification, for example. And we still haven't covered in detail how we do classification with a neural network, and we'll get to that as soon as we start the in-depth lecture, which should be in about 20 or 30 minutes. Okay, so if you remember from the PyTorch lecture, there's this thing called nn.sequential, which lets you define a neural network or kind of set up a neural network in PyTorch. And here it's not defining so much our whole neural network as just the end, the head of our neural network. And there's a few things we're doing here. Again, I don't want you to worry about them in too much detail. Don't worry about these steps too much right now. You may need to dig into these as part of your project, for example, and somewhat as part of your programming challenge, but don't worry about them too much yet. We'll get into this as well, and we'll also get into this, but I really just want you to look at really just 2 things. I want you to look at this layer, and I want you to look at this layer. Does anyone remember, what does nn.linear do? What is nn.linear? We covered it in the PyTorch lecture 1 week ago. What is nn.linear in PyTorch? What does that create for us? Any ideas? So we've got a good guess. So Sai says linear transform. Yeah, so I like Hernan's answer so far, makes sense. So if you remember in our neural network series, right, we had multiple layers, and each layer is what we would now call fully connected. So all the input units are connected to all the output units. What nn.linear does is it makes a layer of a neural network. Is what it really does. There's other kinds of layers, which we'll get into more later. But this is a basic layer of a neural network. And what we're doing in the head of this neural network, kind of just the end of it, so applies a linear transformation to the incoming data, we are putting 2 additional layers on the end of our neural network. And I'm not too worried about a bunch of the stuff in here. We'll get to it. But I really want to focus on one little number right here. So you see the very output. This controls the number of output neurons, this very last number. So why is this 4? That's my question to the class. Why is this 4? Any ideas? Why do I have a 4 for the very last dimension of my output? Yeah, exactly. We have to predict 4 things, right? We need to predict 4 numbers, the coordinates of the bounding box, right? So I needed to predict 4 things. So I'm going to make my neural network, I'm going to make the output 4, right? 4-dimensional. So this is going to predict 4 numbers. Okay. Now, I have to do something a little bit special here. So I have to define a loss function. And again, I wouldn't sweat this too much right now, but I want to show you a little bit under the hood here. So this is a custom loss function in fastai. Really, it's written in PyTorch, but we're plugging it into a fastai learner. And what this is this is how we measure our loss. So our data loader is actually going to hand us a few different things. It's going to hand us what's called output. This is like the output of our neural network, which in this case is going to be just 4 numbers. And it's going to hand us what are called the bounding box targets and the classification targets. So our data loader knows both the coordinates of the bounding box and it knows the class. It knows both, right? So it's going to give us both of those things. But right now, I'm just saying, hey guys, let's just focus on the bounding boxes. So if you look carefully, what I'm doing here is I am computing a loss function in terms of the network output and the bounding box targets. So have a look at this line for a second. And I see a question that's coming from Sai. It says, are there any predefined loss functions? Yeah, so Sai, absolutely. So if we look back, so Sai has asked, are there predefined loss functions? And the answer is definitely, and you probably most of the time can just use a predefined one. What I'm kind of trying to show you now is how to customize things. But if I go back to, this is, actually, let me do that. Well, no, I can't run 2 at once. That's annoying. This is my notebook this is the classification in fastai notebook. It's a notebook 2 from our lecture series. Here, notice that I have not given my learner, I have not told it a loss function. fastai will actually automatically pick one for you, and you can figure out what it is by typing, I think it's learn.loss, or loss func perhaps. It's going to pick which one it thinks is appropriate. In this case, with the bounding boxes, because what we're doing is kind of custom, it's not going to know what to do. But in general, yes. Usually you don't have to even tell fastai, and it will take a good guess. So yes, there are predefined loss functions. Really good question. So here, I can't use a predefined loss functions. Yeah, that's right. fastai is pretty cool, right? It's going to pick one automatically, yes. And that works sometimes for the most typical cases, but not always. In this case, we couldn't get away with a predefined one. We'll talk about unsqueezed later if we need to, but the only thing I want to focus on with you guys real quick is L1 loss. What is L1 loss? Can someone give me just a quick description of what L1 loss is in the chat window? So type 1, yeah, I see some okay. Give me some, how would you explain it to a student, right? To someone who is learning about machine learning. How is it different than L2 loss? Yeah, thank you, Abhijit. That's great. Cool. So L1 loss, really, all we do with L1 loss is we're going to take the differences. So this is, at the end of the day, this output is 4 numbers. It's the 4 predictions, and these are the 4 target numbers. L1 loss says just take the difference, so take like this minus this, and take the absolute value. That's all we do. If we were doing L2 loss, which is also known as the square error, which is very closely related to the mean square error, we would take the difference and we'd square it. And then L3 loss is the difference cubed, and so on. So L1 loss it's a good loss to use on problems like this. It's just the difference of our 2 signals, and take the absolute value. Why would taking the absolute value be important for a loss function? Any ideas? Why would we want to take the absolute value of the difference? Why not just take the difference? Yeah, thank you, Hernan. So negative values, right? So if we get a negative value for the loss, that appears that we're doing better actually, right? But if the target was 2 and the prediction was 1, our loss is 1. But if the prediction is 1 and the target is 2, our loss would be -1. But that's just as bad, right? So taking the absolute value makes some sense. We'll get into that more later too in detail. I want to show you a really cool fastai function called learn.summary. What this does is it actually walks you through every single layer in your neural network, and it shows you the shape of your data as you move through your neural network. So this actually walks through and shows you how, and we'll get into this more when we talk about convolutions, but this shows you how the data is passing through every single layer. Each of these com2ds is technically, well, really these 3 things together make up a layer. We'll get into why that is today or on Thursday. But what I really want to show you, I think, is the head of our network. So we have all these layers, 34 of them. And at the very end, why do I have 2 of these? Oh, because I'm doing max and average pooling. That's not too big of a deal. But what I really want to get to is at the end of the day, we're predicting 4 numbers. And you get some nice summaries here. So this neural network that we are about to train has 25 million trainable parameters, which might sound like a lot. Oh, sorry, it has 4 million trainable, excuse me. It has a bunch of non-trainable parameters. We'll talk about why that is when we have a chance to. And notice we're using the Atom Optimizer. We're going to use the Atom Optimizer. And fastai has chosen this for us. That's cool. And we're going to use weight decay also, which fastai has also chosen for us. So remember that with fastai, it's going to pick a lot of the things automatically for us. And it takes good guesses usually. It's not always perfect, but the guesses are usually pretty good. But the one thing it doesn't guess for you is the learning rate. And we use this nice method called LR-find usually to find a learning rate. And I'm just running LR-find now, and this should help us find a good learning rate. So this should make a nice plot for us in a minute. Let's see, it's taking about 11 seconds per epoch. It's going to try 10, so we've got a little bit of waiting time. And that's okay. Let me ask the class one question while we're waiting. This unfreeze thing, who remembers? What does this freeze unfreeze thing do? So while we're waiting on LR-find, does anyone remember what does the freeze unfreeze thing do? Yeah, so frozen weights. So Abhijit is correct. Why would you want to freeze your weights? Why is that? It seems if you want to learn, shouldn't your weights be unfrozen, right? Why would we want to freeze our weights? Yeah, so not change the base model. Yep, great. So, these networks are separated into kind of a backbone and a head, or a tail and a head. And the idea with freezing is we only train the head. We only train kind of the end of the network. And it turns out we can get better performance that way, and we can converge more quickly. So that is the idea here. And what I really want to get into, I want to make sure we have a little time to talk about multitask learning, because that's going to be a big part of your programming challenge, is to set up a multitask learner in fastai. So let's see, how is LR-find doing? I think we're almost there. We've made it through 8 epochs. In anticipation of this next lecture, maybe being a little slow, I'm going to go ahead and run all for the next notebook, which is notebook number 4. I'm going to go ahead and run this thing, so when we get to it, hopefully we'll have it run already. Okay, but it'll still be live. Okay, I think we finished, I think. Let's see here. Maybe it stops early sometimes when it detects this condition. Okay, so here's our plot. Let me ask the class. Based on this plot, what do you consider to be a good learning rate? Right there, cool. Throw it in the chat window. What feels like a good learning rate based on this plot? Yeah, so I like 1e minus 2, I agree. That puts us about here. We could be a little more aggressive. We might be able to go, I think I saw a 5e minus 2 from Abhijit, I agree. So maybe we go up to here, something like that. So yeah, let's give it a shot. Let's try to be, I usually like to be a little more conservative, but you know, feel free to experiment. You may be fine, but I'm going to try 1e minus 2. And we'll train for a little bit and we'll see how we do. This task is going to be a little bit harder because we're not going to be measuring accuracy. There are some metrics we could pull in, but here we're just measuring loss, which is, remember, it's that L1 loss. So it's hard to know if this is good or bad. It is in pixels, so you could say, okay, actually it might be, no, it's normalized, sorry, this is not in pixels. So it's going to be hard to know if we're doing well or not just based on this number, but you can compare these two numbers to see if we're overfitting, right? And notice that my valid loss is less than my training loss here, which is a good sign. So I don't see too much evidence of overfitting. Here it looked like maybe that's a little bit suspicious, but it was still early in training. So, and wow, that was a nice step. We really learned a lot in that epoch. That's great. And what is an epoch again? Just throw it in the chat window. What is I just used that word epoch. What is an epoch? Yeah, so it's an iteration. Be careful. If this was a quiz, I wouldn't take just the word iteration because I need more detail. So I think Abhijit said it well. He said it's one iteration through the entire data. I might use the word pass through the entire data because the word iteration implies just one gradient descent step, and that's not really what an epoch is. So an epoch is one pass through the training data, and be careful. So it's not the number of times we pass through the training data. An epoch refers to one pass through the training data. So in a sentence, I might say, well, let me use it in a sentence now. So I'll say, okay, this network has been trained for 6 epochs It's been trained for 6 epochs, so 6 passes through the training data, and now it's being trained for its, sorry, 7. It's been started at 0. So this network's been trained for 7 epochs, and it's about to be trained for 8 epochs. So an epoch is 1 pass through the training data. Okay. So you can see our loss comes down. That's great. And it looks like I do some more training. That's great. I'll train some more if I need to. I kind of want to visualize and see how we're doing. So I've written a little visualizer here that lets us visualize our performance. I'm thinking we probably want to train more, but here it is. Let me just show you. So the yellow or the green, that's our ground truth. That's our label. And the blue is the prediction of the model. And I've only trained it for 7 epochs. I haven't unfrozen. I haven't used a lot of the tricks that are available in fastai. Like I haven't run this cell that uses, sorry, hold on. I haven't run this cell yet that uses cyclical learning rates. And I haven't even unfrozen. So really, I would think that I'd unfreeze right here. Let me do that real quick. Learn.unfreeze. Cool. I may run that in a minute. But already, like, we're not doing terribly. So the bounding box is kind of in the right neighborhood. It's not great. Here it missed. But overall, you can see that it actually is learning something. And a lot of times, if you don't set up your network right, it won't learn anything at all. So doing those visualizations early can be really helpful because they can reveal problems early on. So I would recommend doing that. And I really should have done another LR find. Notice that I've really cranked down the learning rate here. I may have done an LR find earlier when I was experimenting, but I really should have done that again. But I'm going to go ahead and train for a little bit longer, and we'll see if we can improve performance. Our best validation loss is 0.13, so we'd like to see if we can get better than that. Another nice thing with fastai is this learn.save. So what this does is if you want to run some experiments, like let's say you want to try a higher learning rate, but you don't want to lose your previous weights, you can do a learn.save, and then you could train, like let's say I wanted to try a way higher learning rate, right? I could make a cell down here. I could crank this way up to like 100, which I wouldn't recommend, but you could. And then if this goes terribly, if this doesn't work very well, you can just do learn.load, and it will restore your previous weights. So that's a really nice option to have. You can, oops, load, there we go. This will allow you to restore your previously saved weights. Okay, so as I've been talking, our model has been training, and then Colab seems to agree with me today, so that's good. So let me see here. I'm going to comment this and comment this. All right. So yeah, look at that. This error is coming down really nicely. We made it down to 0.059. We started way up at like 0.9. So the model definitely appears to be learning. We don't see evidence of overfitting, which is exciting. And yeah, this is going pretty well. So I hope that when we visualize our new results, those bounding boxes look better. That will be a really an important test. So we're almost there. We just have, I think, 1 epoch left to go, and we'll see how we did. So let's see here. Hopefully we get a nice low validation loss. Yep, nice and low, that's great. I'm gonna save these weights just in case, and let's visualize them. So I'm gonna make a batch. I'm going to visualize it, and feel free to come review this code later if you'd like to. This kind of has some details about how you get this stuff in NumPy. But yeah, look at that, right? So it's not perfect, but hey, we just whipped it up in fastai really quickly, and it's not bad. So you can see it's still missing here. That kind of sucks. This is not great, but they definitely got better. So you could imagine that if you spend more time training this and tweaking things, you could probably do better. So that's pretty cool. Hopefully that makes sense. You know, we've improved our performance. Now, the last thing I want to really show you in this lecture, well, really 2 things. There are 2 different ways to save your results in fastai. So you can do learn.save, and that just saves your model weights for you, so you can return to them if you'd like to. There's also learn.export, and this saves both the weights and the model, like the model architecture. And I believe in your programming challenge, you'll be using, I believe it's learn.export. Yeah, it must be. It must be learn.export. So this is, I believe, what you'll be turning in. Oh yeah, great question. What is .pkl? Yeah, so PKL stands for pickle. It's kind of a fun name. It's how Python, it's Python's built-in serialization library. If you want to save something to disk, Then a pickle is kind of the built-in Python way to save stuff to disk. Great question. Okay, so before I finish this little lecture on bounding box detection, I want to show you one more thing, which is this idea of multitask learning. And maybe like 3 weeks ago in the autonomous driving lecture, I showed you a video of how Tesla does some of their vision, how they do some of their computer vision. And I wonder if I can pull it up quickly. I might be able to, but maybe not. We'll see. This probably won't load. But I'll try to load it while we're talking. So if you have a system like Tesla does, and they are interested in predicting lots of different things, so like bounding boxes around cars, lane markers, they want to know something about the ground plane that they're traveling over, all kinds of stuff. You could train a neural network for every task. So you could say, you know, one neural network for lane detection, one neural network for car detection, one neural network for steering wheel angle prediction, you know, all kinds of stuff, right? It turns out in practice that you can actually get better performance and have a bunch of other advantages if you train one neural network to do a bunch of different things at once. This idea is called multitask learning, and this is going to be the focus of your programming challenge, is you're going to solve a neural network to do 3 things at once. So it's going to classify an image as a brick ball cylinder, it's going to find a bounding box, and it's going to segment. It's going to provide a segmentation mask, which I'll show you in a minute kind of how that works. But just to give you a sense for kind of the work that you have cut out for you with this programming challenge, I want to show you how to do multitask, or how to do 2 things at once for bounding boxes. So here, notice that we have not predicted brick ball cylinder, right? We've only done a bounding box. So now I'd like to show you how to do 2 things at once, right? And you're going to do 3 for your programming challenge. I would like to show you how to do the bounding box and the classification at one time. So let's get into that. So how does that work? So we're going to load up some data just like we did before. You'll have to mess with this data loader a little bit as part of your programming challenge. That should give you some nice experience with fastai. So here's our data, nothing too exciting. What I really want to get into is this. So this is the new loss function that's going to allow us to do 2 things at once. So our data loader is going to, actually, there's one other thing. Maybe we'll talk about this first, although I kind of want to ask you. Yeah, let me back up for a second. So how to set this up exactly? So to do bounding box detection, we had to predict 4 things, right? And it's 2 coordinates for each edge of the box, right? How many things do you think we need to predict to be able to do bounding box detection in addition to classifying if something is a brick, ball, or cylinder? What do you think the dimension of our output should be? So throw your guess in the chat window. What do you think the dimension of our new neural network is going to be that has to predict both the coordinates of a bounding box and brick, ball, cylinder? So I see a 5, great guess. I see a 7, I see a 9, right? Okay, good guesses. So the answer here ends up being 8. It ends up being 8, and we'll talk about why soon. It turns out what you want to do, or a good strategy, is to have 4 extra numbers you predict, and basically you have one number you predict for each of the separate classes. So we'll get into why you do that in today or tomorrow or Thursday's lecture. So you have 1 for brick, 1 for ball, 1 for cylinder. And it also turns out it's helpful to have it's called like a background class. So a class that you would use if there was nothing there. I think in practice, in this example, you could get away with not having that because your images always have something. But in practice, when you're doing detection, you want to have that kind of background class. So that's why it's 8. So we want to predict 8 things. And if you look at my neural network, wow, look at this, I'm predicting 8 things, right? So that's the idea. And I think I kind of want to start this thing training. So I'll keep talking and I'll share how this thing works, but I want to show some results. So I'm going to go ahead and start this thing training. I'm just going to run a bunch of cells. Cool. And that'll all run and we'll talk a little bit more. Yeah, so Sai says, but they all come under one class or no. So not really, Sai. We will get into that when we basically, you know, here's our, here is, So today we're supposed to get into, and we'll get into deep learning in depth, and we will talk in detail about this idea of a cross entropy loss function, and we'll discuss about how they come together. So yeah, it's a great question, Sai. Right now, I don't have the visuals I want to show it to you in detail, right? So just wait until we get into this lecture, which will start it today, and we might not get to cross entropy till Thursday, but you'll see how they come together. It's a really, really good question. Okay, cool. So the last thing I want to show you guys is kind of how do you put this stuff together, right? So I want to talk about this. So please have a look at these two lines of code with me. And just take a minute and see if you can figure out what I'm doing. I know that some of this is like PyTorch and fastai, and it's kind of new and weird, but you guys are smart, and you've proven that again and again. So have a look here and see if you can make a guess at what these two lines are doing. Once you have some kind of guess, throw it in the chat window. What do you think? What am I doing? What's happening? What are these two lines? Yeah, so Abhijit just said it really well. So the first thing, which I'm calling DET loss, this measures how close our bounding box is. It still uses that that L1 loss, right? To Abhijit or to anyone, what's going on here? Why am I doing y hat of colon comma colon 4? What is going on here? Yeah, so I'm taking actually the first four. It's kind of funny. I'm just taking the first four output values and I'm saying these four are going to be for the bounding box and the next four are going to be for classification. What's kind of funny is there's something significant about them, right? I could switch those. I could say the second four for bounding, but the network will learn whatever we set up, which is really, really cool. So I'm just saying, let's take the first four predictions, and it's usually across a mini batch. So I would take all the rows of the matrix and I'd take the first four columns and call those the bounding box predictions. So I'm calling this the detection loss. So detection is the word that gets used in deep learning to describe the process of not only classifying, but we say detecting to find a bounding box, basically. This is our detection loss. I could say detection bounding box loss. And then this loss is our classification loss. And we'll talk about this loss function, the cross entropy loss. It turns out this is a better loss function for classification. And here, just look, I'm taking the second four, right? So I'm just splitting the output into two. And I'm just taking those two losses, and those losses will come together to make an overall loss. Two more questions for you guys. What is this? I mentioned this very, very briefly when we started talking about PyTorch. Does anyone remember, what does dot view do? What does dot view do in PyTorch? What is it the same as in NumPy? Good guess. It's not the last value. Yeah, so you're very close. Your answer is pretty solid. So it's the same as ravel. It's the same as ravel. So in NumPy, you know, we have this method called ravel that unrolls the matrix into a vector. That's what view minus 1 is doing. So we just have to do that to make the dimensions match. But I have one more question for you. So notice that I put that my total loss, my loss function, is equal to the detection loss plus 1 times the classification loss. My question to the class is, when would I change the 1.0? Like, is that 1.0 doing anything? Does that make sense? So see, I'm returning the detection loss plus the classification loss, and I'm multiplying the classification loss by 1.0, which obviously isn't doing anything, right? 1 times something is something. But yeah, so I'm balancing the importance. So let's say we trained our model, right? And let's say I came back and I said, oh, I wish that this was 10, right? What kind of problem with our model might that address? Making this 10, right? What should that make the model better at? In theory. Yeah, it should be better at classification, right? So if you like have to get your classification right, but your detection doesn't matter that much, you might do this, right? So it changes the relative importance of those two types of error. Okay, great. And I'm going to measure, so in fastai, there's an idea of a loss function, which is what this is. This is actually the signal that's used to train our neural network. And there's also the notion of a metric. And metrics, these are just what gets printed out as we train, just so we can measure and look at our performance. And we're going to look at the accuracy, which is going to be just the, I'm going to use a built-in metric called accuracy from fastai, and use the classification targets and the first four values, the last four values, which we're using for classification. And I'm also going to look at the L1 loss. So these are the things I'm going to look at while I train. And let's go ahead and look at some training. So here we go. Here's some training. Oh yeah, and we've got some not a number. Oh wait, that's the that's the learning rate finder. Okay, cool. So I found a learning rate. I trained for a while. Here we go. This is what I wanted to look at. So after 4 epochs, our L1 loss is coming down pretty nicely, and our accuracy has actually bumped up to 97%, which is pretty cool. I think I unfroze. I did LR find again. Here's my plot. I put down my learning rate. I could have gone a little higher maybe. But here we go. And look at that. For the first time, we're seeing an accuracy of 100%, which is pretty cool. This won't always happen, but what happens sometimes, you would think that a multitask network may not perform as well as a monotask network. But in some cases, you actually get better performance because the backbone is learning from multiple signals now. So it has like multiple types of data to learn from. So in some cases, multitask models do better than single task models. Okay, so we're learning, that's great. We're gonna look at the results in a minute. We may hop to the next lecture and we can come back and see how it's doing, but it's training. And what you'll see at the end here in this notebook is you'll see this model predicting both the class and the bounding box together. It will be doing both tasks. And for your programming challenge, you'll be doing 3 tasks. So I've shown you 2, you'll be doing 3. Okay, so we'll do a quick walkthrough of image segmentation, and then we're going to go into today's lecture. We're a little bit behind, but that's okay. We have an extra lecture planned in the deep learning module. We may end up using it just to kind of get through everything. So I'm going to let this keep training. We'll come visit it in a minute. But in the meantime, I want to talk about semantic segmentation. So this is yet another thing we can do with a deep learning model. And I went ahead and ran this notebook as you guys were watching me lecture on the previous notebook. And in segmentation, this is what our label looks like. So here's our image, right? And we've seen different kinds of labels. We've seen classification labels. We've seen bounding box labels. In semantic segmentation, your label is actually an image. And what you're trying to do here is you're trying to capture every pixel in the input image that corresponds to your object. So it's a very precise type of deep learning, of modeling. It's called semantic because we're not just predicting where the object is, we're actually also predicting a class. So semantic has to do with like a name. So we're predicting that, hey, all these pixels are where there is a ball, basically. So we're not just predicting the pixels, we're also predicting a class for each pixel. So we'll get into that into more detail here. Just know that there's also something called instance segmentation. So in instance segmentation, if there are 2 objects that are discrete objects, like 2 people, you would want to separate those from each other. So you'd have like person 1, person 2, as opposed to semantic segmentation where you would just have a person class, basically. So similar, but they're a little bit different. So as far as the labels I've given you here are PNG files, and those represent the, it's these masks, basically. We call them masks. Notice here that I'm setting up my classes for my model. So the model is going to have a brick, a ball, a cylinder, and then also a background class. The background class is really important because some of these pixels are not going to have a ball in them, or a brick, or a cylinder. They're going to be just background. So this lets us predict that with our model. I won't talk about the data loader too much. This is the fastai data loader. There's an object called a semantic item list or segmentation item list that lets us hold 2 sets of images and feed them into our neural network. Nothing too exciting there. I won't discuss this in too much detail. Please have a look at this as you do your programming challenge. Here is a visualization of our data loaded up to train our model. And we've highlighted the pixels that correspond to the labels. So you can kind of see that all the objects are glowing. And I think I do want to show you one more thing, actually. Yeah, how can I show this to you easily? Okay, here's what I'd like to show you. So just to give you a little bit more sense of how this model works. So here's what I want to show you if I can get a new cell. There we go. So what I want to do is I'm going to load a batch. So I'm going to do x comma y equals data dot one batch. And what that does is that loads one mini batch of training data. And I want to have a really careful look at the dimensions of the input and output tensors. So I'm going to look at x dot shape, and I'm going to look at y dot shape. And I want to talk about why are these the shapes. And I think that will give you hopefully just a little deeper understanding of how this segmentation mask or this semantic segmentation task works. So this is the input. So 16 by 3 by 256 by 256. That's the dimension of the input. So in the chat window, please, if you have the answer, let me know. Why is this the dimension? Why is our input 16 by 3 by 256 by 256? Any ideas? Yeah, thank you, Abhijit. So the 16, we're doing mini batches of 16. So this is one little batch of data. There's 16 images in it. We put the color channels first. This is a PyTorch convention, so you might be used to seeing like 256 by 256 by 3. That's how OpenCV does it. That's how Matplotlib does it. It turns out it can be a little more efficient to do it this way, so PyTorch switches the order on you. And the images are 256 by 256. Great. And look at my output now, my target, right? So I still have 16 because I have 16 images in this batch. And there's kind of like one color channel, right? So this is going to contain, basically it's going to contain a 0, a 1, a 2, or a 3, depending on which of the 3 classes we have. So that is, and actually I can maybe go a little step, for fun, let's do this. So I should be able to do like y of, let's look at like the 5th example, y of 5, comma, 0, comma, colon, comma, colon. So yeah, I'm just gonna, what I wanna do is I wanna say, can I have a look at one of these examples? So let's try it. So this is a tensor right now, and I think it's on the GPU. So I wanna turn this into a NumPy array. So I believe I can do CPU dot NumPy. I think I'm missing something. Let's try it. Let's see. Oh, that was easy. Okay, cool. And I'm gonna try to IM show this. So here is a look at the, yeah, there you go. So there's the 5th label, right? So you can see there it is, it's a bounding box. It is a, sorry, it's a segmentation mask for a brick. I wanna do one more little thing here just to show you what's going on. So I'm gonna do .unique. So .unique, which is gonna fail, of course. Yep, great. So I think if I do np.unique of this, it'll do what I want. All right, there you go. So this is made of zeros and ones. What I really wanted to push on a little bit, and if this doesn't work the way I thought it was, then I have a problem. Maybe I do have a problem. That's weird. Oh, am I just doing segmentation? Oh yeah, that's interesting. Okay, cool. Did I mean to do that? Maybe I did. Interesting. Okay, what I was trying to get at here is that I claimed at the beginning of lecture that, or at the beginning of this lecture, that I was going to predict the class and the location, but I think here I'm actually only predicting location. That's interesting. Am I ever going to do that, or am I leaving that to your challenge? I may be leaving it to you for your challenge. Oh, no, I'm doing it here. Yeah, that's weird. Okay. So we may save this for next time because I do want to hop into the next lecture. But what I wanted to make sure I showed you, there's just a couple of things. So let's place a hold on this for now because hopefully it makes sense what I'm confused about. I'm confused whether or not I'm showing you how to predict the class and the mask or just the mask. So we'll come back to that in a minute. Did I just leave something out though? Is it actually simpler? Oh no, okay, good. Never mind. All right, I'm not dumb. Okay, good. Or at least when I made this notebook, I wasn't dumb. Okay, what I was really looking for is, yeah, I just forgot to update that. Okay, cool. So if I go to example number 8, this is a cylinder. The encoding for cylinder is 3, right? And what I was looking for, I wanted to make sure that that mask actually contained values of 3, right? So if you look back, right, so like brick is number, or there's a ball, I think. So if I go to example number 6, yeah, so ball is 2. There we go, cool. And then so the class is like encoded as the number in the segmentation mask. So yeah, that's perfect. So if I have a brick, for example, the label we end up with is all zeros. This background is all zeros, then it has ones everywhere the brick is, right? And if I have a cylinder instead, I think this is cylinder, I believe. If I have a cylinder, we still have zeros everywhere, but the region where the cylinder is going to be encoded with threes. These are all threes. So that's how we tell the neural network. We get it to predict which class by encoding that number. The number that we put in that pixel location corresponds to the class. I hope that makes sense. If not, come back and look at this code a little more closely, but it is doing what I thought, so that's good. So here we're going to have a more complicated custom head, as you may have guessed, because let me just go back here for a second. So, now that you kind of know what our task is, in the first example I showed you, we had to predict 4 numbers, the 2 coordinates of the bounding box. In the second example I showed you, we had to predict 8 numbers to do classification and regression to find the bounding box coordinates. How many numbers do we have to predict now, right? So what do you think? Like, what is the dimension of our output to solve segmentation, right? What would be the dimension of our output in this case? Yeah, so it's the same as Y. Yeah, so it's this. It's actually 16 by 1 by 256 by 256, right? So we have to actually modify our network to output an image, right? To output an image, which may sound hard, but it's really not too bad. So again, I won't get into this in a ton of detail, but it turns out you can use this thing called a transposed convolution, and that allows you to take a neural network and kind of, usually we'll get into this more, but neural networks kind of take their input and they make it smaller and smaller and smaller. This lets you take your some point in your network and make the output actually bigger. So that's what I do here. Basically, is I set up this transposed convolutional thing, and I use this to create a custom head, which creates an output that is equal to the size of the input eventually. And again, I'm going to define a loss function. In this case, it's going to be this thing called pixel accuracy. And I'm going to give it this custom head. And what we end up doing is it's the same exact pattern for training. We LR find, we train our model. And at the end of the day, I'll go ahead and hop to the result here. And as part of your programming challenge, you'll have a closer look at kind of the details. But this is what we end up with. So we end up with a model that can predict the class of every pixel. And I think the thing that I really want to emphasize is, even though I've shown you 3 different tasks in FastAI, how similar they are. So for each one, we basically have to go in and invent or develop a custom, what's called a custom head. And we have to maybe come up with a loss function. But other than that, like, everything else is the same. And that's kind of the power of FastAI, is that if you kind of know how to use the library and how to plug stuff in, it's kind of this big unifying framework where, how many lines of custom code did I have to write to do segmentation? Well, if we kind of count them, I had to write 3 here for a loss function or for a metric. I had to write 4 and then 5 lines of custom code there. And then for my data loader, this is fairly standard, but I had to write a few lines. So, but anyway, to do a completely different task like image segmentation, I only had to add maybe 10 or 20 lines of code. It'll take you some time to figure out what lines to add, but the fact that you can do that in so few lines is really, really powerful. And it's something that I hope sinks in as you work on your programming challenge and hopefully on your course project too, if you're using deep learning. And then finally, I just wanted to say one more thing. Oh yeah, this is really cool to me too. So for all 3 of these tasks, we're using the same backbone. I've switched here to a ResNet 18, which is a shallower model, but it could have been a ResNet 34. I could have popped that in easily. So these deep neural networks are so general that we can take the same exact backbone, change the end of the network, and do a totally different task, like segmentation. So they're kind of becoming good enough that they're like general learners that can learn all different kinds of tasks. It's just a matter of getting your data loader figured out, your loss function figured out, and any kind of customization you have to do to your neural network. So I know I've thrown a lot of FastAI at you and we only have a few minutes left, but I do want to start the next lecture. But really the point of your programming challenge is to get you deeper into FastAI. I hope you've enjoyed what you've seen. It really is just an incredibly powerful library. Like I said, I use it every day at work. And I believe it is kind of the I think it is the state of the art in deep learning. And one other interesting thing about fastai is it's a lot of people either don't agree with me about that, or they just don't care, or they haven't spent time with fastai because it's not nearly as popular yet. I like to think that fastai is just becoming popular, and in like 3 years, everyone's going to use it. But we'll see. So hopefully I'm right, and you're at the beginning of a trend, that will continue to grow. But you'll talk to lots of data scientists who don't use fastai, which is interesting. So I promise it's worth your time, but don't anticipate that everyone will have used it. But I found in my own work that using this can be a huge advantage. I can get stuff done faster than folks who couldn't, and I can get better performance than a lot of folks who wouldn't use fastai. So not in every case, obviously, but for me, it has been a really big advantage. So I hope it's an advantage for you as well. Yeah, so Hernan asked, are all ML frameworks similar? Definitely. I would say fastai is just a little more opinionated. It takes some different design decisions than Keras, for example. And they all have strengths for sure. So there's a lot of similarity, but I do think that fastai really gets some things right that I haven't seen other frameworks get right. But that's just my own opinion. I'm going to have a strong opinion about it because I work in the field and teach in the field and stuff. So yeah, that's just a summary. I hope that's helpful and helps you on your project and programming challenge. I want to spend the last 10 minutes. I know we're going a little bit faster, but I want to kind of get you into a little bit more depth. And I changed the title of this lecture, but I must not have pulled yet. So this is really deep learning in depth. Because I've just shown you a bunch of stuff that fastai can do, and I'm anticipating that you're going to use fastai as part of your programming challenge. But I want to get you under the hood a little bit more, so you understand, what's all this stuff I'm throwing at you, what is cross entropy, stuff like that. So for the next 2 lectures, we're really going to kind of back up a little bit and go deeper into how these deep neural networks work. But fastai really is, this is a case where for your programming challenge, I've shown you everything you need. So you've got a couple weeks still to do, and you've seen really all you're going to see about fastai. Please do ask questions. I know that I kind of glossed over some of the segmentation stuff. The notebook should be helpful. And then if you want to go deeper, the fastai course it's really, really good. So that's the wrong link, but we have a link to it in the notebook. So you can hear Jeremy Howard teach this stuff as well. That's not a requirement for this course, but it is helpful. I might have put it as part of your reading. Let's see, did I? Oh yeah, I asked you to watch lecture 1. So yeah, hopefully you've seen lecture 1. The fastai course is really great. Okay, so let's take the last few minutes, and now I want to kind of slow down a little bit and really get into the details of how we go about solving training these deep neural networks, because I really glossed over a lot of those to kind of give you the most up-to-date tools. So we actually really glossed over this. I never told you, how do we use a neural network to solve a classification problem? Because if you remember in our neural networks demystified series, we solved a regression problem. And fastai kind of does this under the hood for you magically, right? So I want to talk about what is it actually doing. So we're going to use this data set called the MNIST data set, MNIST. And this is a bigger data set than we've worked with before. It consists of 60,000 images of handwritten digits. So on the left here, this kind of represents the data set. And on the left is an image of a handwritten digit. And on the right is the label. So we have 60,000, actually 70,000 images and 70,000 labels. So this is a data set that's nice and small compared to bigger data sets out there that we'll use to train some models and to learn a little bit more about how this stuff works under the hood. So I'm going to download this data set. It's available at this URL. So I'm going to download it and unzip it onto my local computer. And I'm going to load it right up. So here is the data set. So if we look at the dimension here, so this is x train, which is our x, our independent variable. So look at our dimension here. It's 50,000 by 784. Basically, these are all our images, and they're unrolled into vectors. So if I reshape those, and they turn out to be 28 by 28 images, I get the images here. And these are handwritten digits. And for each of those, I have a label, and I'm showing it here. So this is a 4, and the label says 4, and this is a 1, the label says 1. So that is our data set. And I plotted just a couple of histograms here. It can be helpful to look at your distributions. So this is the distribution of our data. It's not exactly just black and white. So these are the white pixels over here. These are the black pixels over here. And notice there are shades of gray. There are some shades of gray. So that's the distribution of our our input values. This is the distribution of our output values, which can also be helpful to look at. We would hope that this is uniform because this is the frequency at which each label occurs. So we see we have a little more ones than we have zeros, for example, but it's pretty uniform. So that just gives you a little feel for the MNIST dataset. And now really what these next two lectures, this lecture and Thursday, are going to consist of is we're going to take all of the kind of fancy stuff that makes modern deep learning work, and we're going to break it down one topic at a time. And the first topic is going to be stochastic gradient descent, which is the way we've been training networks in fastai. And I'm going to reference what I think is the best deep learning book out there. This is one of the 4 books for this course. It's not required that you buy it or anything, but it is available online. And I do have some readings. I think last night, yeah. So last night's reading was from this book. And this book is really, really good. I highly recommend this book. It's a little more theoretical, but it's excellent. So we'll be referencing this book and a couple other sources as we get deeper into how modern deep learning works. So first, let's talk about stochastic gradient descent. And if you remember back in the Neural Networks Demystified series, we actually did what's called batch or deterministic gradient descent. That's where you take your whole data set, you compute your gradient from your whole data set, and then you use that to drive your optimization. In practice, it's going to be, once your data set gets big, you're not going to be able to fit it into RAM, so you have to break it apart. And it turns out that breaking it apart has other advantages. And when you do that, it's no longer called gradient descent or batch gradient descent. We use the names mini batch or stochastic or mini batch stochastic gradient descent to refer to this idea of breaking apart your data set into samples and then processing those samples one at a time. So you noticed that in fastai, right, there's not a ton of parameters that we picked, but one thing that we did pick is we picked the batch size. So if I look here, nope, hold on. So here, actually no, yeah, there, I picked a batch size of 16, right? So a question you might ask me, you might say, hey, how do I pick this, right? Why did you pick 16? Why not 17? Why not a million? And the deep learning book really has, the reason I like this book is it has very practical, even though it's more theoretical, it has very practical things to help you think through those design decisions. Why do 16, right? So here are 5 tips from the book about how to pick your batch size. So here they are. So the first one is that these are things to take into account. So larger batches provide a more accurate estimate of the gradient, but with less than linear returns. Let's discuss that for a second. So first of all, I hope that makes intuitive sense. So the more of your data you use to compute the gradient, to do backpropagation, the better your estimate is because you're taking like an average of a bunch of stuff. And the more stuff you throw in your average, the more accurate your average is. Hopefully that makes intuitive sense. So the author of this book is this guy named Ian Goodfellow, who's just ridiculously smart. He also invented this thing called a GAN, which we'll talk about in a few lectures, which is how deep fakes work. So he says that larger batches give you a more accurate estimate, but with less than linear returns. What does he mean by that? What does that mean? Less than linear returns. What is Ian Goodfellow trying to tell us? So good guess. Good guess, Hernan. Not quite though. What does he mean? Larger batches provide a more accurate estimate of the gradient, but with less than linear returns. So Hernan guessed that it has to do with overfitting. This does not. Good guess though. Any other ideas? What does he mean less than linear returns in this context? Right, yeah, so Sean is really getting close, yeah. So Sean says change in growth isn't linear with more data. I would like to refine that a little bit. So, because what he's saying is, so what is he saying improves with a larger batch size? What improves? What is he saying gets better with larger batch sizes? So right, kind of right. He's saying that it improves. It says larger batch sizes provide a more accurate estimate of the gradient. So if you have a larger batch size, you're going to get a better estimate of your gradient, which will improve all those things you guys mentioned. But that's all he's talking. He's just saying, hey, you get a better estimate of the gradient. But I want to unpack this thing. This is a very common theme you'll see in engineering and in papers and stuff. So less than linear returns. What he's really saying there is that let's say that you go from a batch size of 32 to a batch size of 64, right? So you double your batch size, right? What he's saying, so if your returns were linear, since if you double your batch size, what this would imply is if your returns were linear, it would imply that you also doubled the accuracy of your gradient estimate. So that's all he's saying. He's saying, you know, if this were linear, because he's saying a larger batch makes for a more accurate gradient estimate, right? But he's saying that if you double your batch size, you're not getting twice as good at estimating your gradient. You're getting something less than that because it says less than linear returns. In practice, it's far less than that. So doubling your batch size may only improve the estimate of your gradient by 10% or something like that. That's what he's trying to tell you. He's saying, you know, maybe you want to pick a larger batch size. Maybe you want 64 instead of 32 because you're going to have a better gradient estimate. You may converge more quickly. But it's not like super powerful, right? It's less than linear in its advantage. So I hope that makes sense. Okay, do have a look at that required reading. So this reading and the Alex note here for next time. These are really, I highly recommend this stuff. I've only given you the reading that I really stand behind. So have a look at that. Next time we are going to dig deeper into the nuts and bolts of deep learning, just deep dives into deep learning. But you have the tools now. So you have fastai. That's what you need to work on your programming challenge. It's what you need to work on your course project in some cases. So I hope that is interesting. That really is the pinnacle of deep learning tools, and we've covered it now, which I'm excited about. So great. So I hope you guys have a good rest of your week. We will talk to you on Thursday. Please get cracking on your projects and shoot an email to Rohan or Arvind if you have any issues, or post an issue on Piazza. And don't forget about Piazza. That is part of your grade too. So do be active on Piazza. So thanks for your time today, guys. We will see you on Thursday.